Alright, what I am going to do next is to derive some alternate expressions for the kinetic energy of an RB with respect to frame F. So recall, by definition, this is what the kinetic energy of a body is, of an RB is. That P is a typical point. I want to derive an expression, an equivalent expression which would be handy while solving problems of interest. And that expression is what I have in the yellow box here. How is it different from the original expression, and how can it possibly be more convenient to use the yellow boxed equation? This equation, the original definition, has integration involved. I don't want to do that integration over and over again. Rather, I want to work with this expression. Okay. So the first term is as if the entire mass of the RB is concentrated at its center of mass. If that is the case, then there will be some kinetic energy associated with the center of mass itself. That's what this denotes, or that's what it looks like. If the entire mass of the RB is concentrated at center of mass, then the kinetic energy of the body would be what I have first term, what I have as the first term here. But that is not all. That is not all. We have another expression which is half times the dot product of omega mf and HCF. Omega mf is the angular velocity of the body. HCF is the angular momentum of the RB about its center of mass with respect to F. Let's quickly prove this. Now to prove this, I don't have to start all the way from here. I'm going to start from this place because I derived it 3 slides ago. Okay. And in fact, in this form of the expression, as far as the first term is concerned, it's already there. I don't have to work on that. I only have to focus on this. Somehow I have to manipulate the second term so that it gives me the second term here. Let's do that. And even there, half factor is already in both of them, so I won't even worry about the half factor. I just want to work on this. I'm going to replace one of these VPCF by omega mf cross RPC. I can replace this. And I would like to take omega mf outside. So again, that A dot B cross C, we will change the order A, B and C. In that way, I think I should replace the second one here. That will give me a more familiar expression. I would rather write it like this. Let it be A, B and C. I want to change A to B, B to C and C to A. Pull omega MF outside, you get RPC cross VPCF. What do we get? This thing, familiar term, nothing but HCF. Okay. So I have been working on this term, right? And I have shown that that equals omega MF dot HCF. So you replace this thing by omega MF dot HCF and you get this. Alright. 90% of the derivation has already been done, and that is why it's very easy for me to complete the next step and get this. Okay. Alright. Another form of kinetic energy expression. Again, all these forms, I am interested in all these forms because it makes it easy to start solving a problem. This form has just one term. The last one had two terms, you see. One term was this, half mvcf vcf. The other was dot product between angular velocity and angular momentum. This one has only one term, half omega mf dot HAF. But then A is a special point. There C was the center of mass. Keep in mind, here A is a special point. What kind of point is that? Of course, A is fixed to RB, but then C was also fixed to RB. So there is nothing new in that way. But then this is the new condition. A is fixed in F also. Keep in mind. A is fixed in F also. So it's a situation something like what I have shown here. This is the RB, it's undergoing some motion, this is the reference frame, but there is one point common to the RB and the frame. An easier to visualize example would be something like this. You have a rod and this is rotating with respect to the inertial frame or the frame here F. Now this point A is fixed to RB and is fixed to ground also or the frame also. In this case, in such scenario, TF is simply half omega MF HAF. Going to prove it. Doesn't take too much effort to prove this. Let's start with the full expression or the general expression, which is always true. Okay. I'm going to write VPF. See, VPF can be written as VPF minus VAF. VF is 0, right? Because A is fixed in F and A is fixed on RB also. I will use that in a little while, but this expression is holds true because VAF is 0, A is fixed in F. But then A is fixed in the RB also. Alright, and if A is fixed in the RB also, then you can write VPF minus VAF as omega MF crossed with RPA, velocity transfer relationship. Okay. So let us use this equation 2 in 1. again that A, B, C reordering you do, I get pull out omega MF dot product, you have RPA cross VPF, but VPF can always be written as VPAF in this case because VAF is 0 and VPAF would be VPF minus VAF. So what do we get? The integral here is a familiar quantity. It's nothing but HAF. I missed this half term here. I realized it only after getting the final expression. Of course, this half term has to be with us all the time. That's what I wanted to prove. Okay. All right. What is next? Next, I want to show, again, I want to derive some alternate forms of kinetic energy of the body when I know my coordinate system, the working coordinate system. So suppose this is the RB and you have this frame F, and I am using this as my working coordinate system. The yellow coordinate system is my working coordinate system, and I am also knowing, I am aware of the fact that the three axes are the P axis of inertia of RB at A. Then I want to see how this whole expression can be simplified. Okay. Now in this expression, as far as this is concerned, this is straightforward actually. VCF dot VCF will be, or rather half M VCF will be simply VCF, can write that as M times V1 square, V2 square, V3 square by 2, where VCF is V1 E1, V2 E2, V3 E3. So that is straightforward, and actually it is not this term why I am actually spending time on this slide. I want to spend some time trying to show you what the simplified expression for this will be. Let's have a look at this. If my working coordinate system is as shown on the figure, with the 3 axis being the principal axis of inertia of the RB at point A. Now, omega mf will be written as this. Okay, and HCF will be written as this. Now keep in mind that SCF would have had 9 terms on the right hand side. In general, 9 terms would have been on the right hand side of this. In general, but right now I'm having only 3 terms because I know that these 3 axes are the P axis. Alright, and thus with this kind of working coordinate system, what do I get? I get this. And thus the total kinetic energy in this coordinate system can be written as still it has many terms, but the terms could have been many more if I had not made this choice of special coordinate system. Special because the axes are the principal coordinate system. And now that we have derived this expression, let's also talk about the 2D problems. 2D problems are the ones in which omega mf is always along E3, and x1, E1 and x2, E2 is a plane of symmetry, right? Now there will be more simplifications. What will be the simplifications? The first thing that you see here, that will not have V3 because it would be planar motion, so you will have m by 2 V1 square and V2 square. And the other contribution that is coming from the angular momentum and the angular velocity, you will have only one term, IC33 omega 3 square. So if you are dealing with a 2D problem, do not worry about all these long expressions that I derived earlier. This should be your starting point. This should be your starting point. Okay. IC33 omega 3 square. Along the same line, let's look at the other expression of kinetic energy when there is a common point between the RB and the reference frame. I derived this expression 2 slides ago. And now I am saying that I want to use this yellow coordinate system as my working coordinate system. What would be the expression of T with respect to F? Like before, it will be this will be the expression. Why? Because HCF should be HAF. HAF can be written as right, and omega MF will be so if you use these two, you should get this. IA11 omega square, IA22 omega 1 square, omega 2 square, and omega 3 square. Again, if the problem is a 2D problem, omega MF is this is a plane of symmetry, A is fixed in F, A is fixed in RB, then what would be the expression? In this case, it would be half I A33 omega 3 square. That's all. Before taking this course in your life, you would have used only this expression. 2D problems. Most of the times, I think in JE problems, there is a common point between the RB and the frame. And that's why this suffices. But now you know that this is a special case. After making so many assumptions, you get to this simplified expression. If not, you don't make all these simplifying assumptions, you will be dealing with this. All right. So what do we do next? Now related to the work energy theorem, there is another concept I want to introduce now, and that is about what we call as conservative force. Conservative force. What is a conservative force? Now, if the work done, this is the definition. I'll write it first. If the work done by a force which is independent of time, which does not depend on time. So I'm only talking about those forces which do not depend on time, neither the direction nor the magnitude. So if the work done by a force depends only on the initial and the final locations of the particle on which it acts, is called a conservative force. So there is a particle P and a force F is acting on it, and the particle moves along a path. So at time t1 it is here, the particle is at time t2, the particle has reached here, and the force has continuously acted on it, and that force might have changed its magnitude, might have changed its direction, as it acted on the particle, but the work done does not depend on the path. It depends only on the initial and final location. Okay, that force is called a conservative force. That it does not depend on time, but it may depend on the spatial coordinates. And since it depends on the spatial coordinates, that's why I am saying that as the particle has moved in space, the particle location has changed, and that is why the force is changing. But if you just focus on this location, the magnitude of the force and the direction of the force will not change with time. Okay. Since the particle is going from one location to another and the force keeps acting on it, that's why its magnitude and direction change. That's what I mean by it may depend on spatial locations. Okay. Now it turns out that if a force is conservative, then the work done by it between work done by the force on a particle as the particle has moved from location 1 to location 2, this is the work done. Okay. And we are saying that does not depend on the path. So this integral will not depend on the particle path. Okay. Let me call this as work done as the particle changes its location from 1 to 2. Now it does not depend on the path, but it does depend on the initial and final location. So I am going to write W12 as difference of the value of a scalar function. Okay, where the initial location 1 had coordinates x1, x2 and x3, and the final location has coordinates x2, x3 prime. A scalar initial location. This is a function. I'm talking about a frame F here, and this is my working coordinate system. Conventionally, we use the symbol V to denote this scalar function. Such that W1 to 2 is written in this manner conventionally. Mind you, there is a negative sign we have put here. Why have we put here? Convention. If everybody agrees from this today onwards that we will write the work done by a conservative force going from location 1 to 2 as difference of S at the final location minus and the value of S at the initial location, we all will be fine. But no, the convention has been to write it like this. Okay. This function V is called the potential function. Or simply the potential. Potential of the conservative force F. Sometimes we also call V as the potential energy. Sometimes we call V as the potential energy associated with that conservative force F. The SI unit and units of V is indeed joules. So if W12 we are going to write as this, and W12 itself by definition of work done is simply this. The right hand side can be written as integral of this scalar function going from location 1 to 2. Which implies that the work done by a conservative force when the particle on which it is acting moves through an infinitesimal displacement vector is going to be this. Negative of change in potential energy or change in potential of a function. Why am I talking about conservative forces suddenly? I will show that if a force is conservative, then the work done by it in the work energy theorem can be the contribution of the work done by that conservative force in the work energy theorem can be written in a more simple manner. And you will see later today or in the next class that the contribution of the work done by a conservative force will actually be written as the difference between the values of a scalar function, and that scalar function is going to be the potential function. But then the question is, how do we know the nature of this function, nature of the potential function, right? So we are led to this question that suppose we know force F is conservative, how do we find its potential function? V. Okay. F is a known force and it is also known to be conservative. So let me write this force as F1, F2, F3 are the scalar components of the force, are scalar components that depend on space, that may depend on spatial coordinates. They cannot depend on time, I have already said that. If a force is dependent on time, there is no question that it can ever be conservative. We are not talking about such a possibility at all. But then I am also not saying that if a force does not depend on time, it has to be necessarily conservative. That is also not true. There are certain conditions and we will look at those conditions also. Okay. Now if this force is conservative, then F dot dr will be minus dv. Right? Since F is known to be conservative. What is dr? Dr is a small change in the position of the particle on which F is acting. So I can write that in my Cartesian coordinate system as, okay, this is my frame F and I have a Cartesian coordinate system here. Particle was here at time t and at t plus delta t it has gone to this location. This vector is dr small infinitesimal dr vector, and I am saying that dr vector can be expressed in general as a small change in x1, small change in x2, small change in x3, and along these three unit vectors, and thus F dot dr can be written as right. On the other hand, dv, which is infinitesimal change in function v as the particle moved from this location to this location. Now this location has coordinates x1, x2 and x3, and this new location has coordinates as x1 plus dx1 okay. These two locations have these coordinates. So my question is that since v itself is a function of the spatial locations, how much change in v will be seen as we change our location from x1, x2, x3 to this location. How much will be the change? This much would be the change. Where these things are called the partial derivatives of v with respect to x1, x2 and x3 respectively. I hope you have studied this in one of the first year math courses. So dv is much. I wish to remind you that of the definitions of these partial derivatives. If I write del v, del x1, what does this mean? This means the following. This is what it means. Pay attention. We are allowing for some change x1, but x2 and x3 do not change. So I measure the difference in v at two locations. One location is the what I call as the baseline location, x1, x2, x3, and then there is another change that another value of v that I am measuring or reporting. This value is at a location where x2 and x3 are the same as the base location, but only the first coordinate has changed by a small quantity, delta x1. That is what is meant by del v del x1. And del v del x2 will similarly mean that's the meaning of the three symbols that are appearing here. Now look at these two expressions. I'll wind up in 2 minutes. Just finish talking about this idea. You look at star, you look at double star, and the fact that star and double star are related through this equation, let me call as 3 star. What do we get? Star, double star and 3 stars give me dx3. But then dx1, dx2 and dx3 are independent of each other and are also arbitrary. Thus, this equation, which I am calling as star dot, thus star dot actually implies that F1 is this. It implies three things. We get a relationship between F, the three components of the force, and the derivatives of its potential along three directions, partial derivative. I stop here. We meet tomorrow at 4.